So we have Ryan Coffey, who's a scientist here, who's going to talk to us about the edge.
Great. Thank you, Elliot, for having me. Tom just finished this talk from the LCF perspective, and I would say I'm going to be very heavily biased toward the sensor perspective. So I apologize if you really live in leadership computing space. I want to connect our sensors to you in a streaming throughput sort of way. The reason I do is because I believe that processing needs to start immediately at the sensor, partly because I think we're in the midst of a revolution where computing is going to be ubiquitous and heavily distributed everywhere. I did a quick data plot and I put $20. My wife and I have traditionally always bet each other $20 on who's right. And so I have $20 that 2025 is this next industrial revolution, and that we're going to have a need for a jump in energy globally that is going to surprise us quite a lot. And so now is important. So I believe there's a high urgency to what we're talking about here, and DOE is sort of the right space to lead the way, because private sector is already doing this. There is deployed AI, and it is going to consume energy at an unbelievable rate, especially because it's going to be ubiquitous, scaled ad infinitum. So I'm very concerned about this. I think it's time to act now. Oh, dear God, it did something weird with that graphic. Well, Jan already showed you this graphic, actually, so I don't have to show it to you. The one on the left. It was the tiled detectors. And the nice thing about working at LCLS is we get a little bit of a preview of what the future is going to look like, because each of those tiles first has to be compressed independently before you can bring those signals together. So this idea that I can see a whole image and make a crystallographic reconstruction from that whole image at the FPGA or the ASIC that's on board that detector, yeah, that doesn't work because those FPGAs are not connected with each other. So we have to be mindful about how we physically instantiate these connected data sources. The other reason I want to show this is because I'm going to think about two problems at the same time. I want to think about LCLS, but I also want to think about the thing that's going to be a piece of the solution, the fusion reactors. And so I focus on D3D. Again, Tom talked about this because there's a lot of effort to that, our nation's premier tokamak reactor. But actually the solutions at the tokamak are going to map to other types of fusion reactors. And talking to even Idaho National Lab, some of these things can actually be implemented in fission reactors as well. It turns out my other $20 is that this jump will be enabled by fission, not fusion. Luckily, because we don't really have a fusion reactor today, this year. And so I think the two are going to have to work together. So that's why I have these two in concert, sort of thinking about two topics at once. And this idea of federated machine learning, I think, is going to be something that is key to all of it. We've been hearing about multimodal experimentation, multimodal this, multimodal that. Well, we have one FEL here in the US, and we have one really great APSU. Those two are complementary sources. If I want to run an experiment in tandem at these two complementary sources, that means I have distributed data acquisition that I need to aggregate in real time somehow, and I would bet there's going to be a security concern here. And this is where the authentication we were talking about comes in. And in fact, data privacy is going to be interesting. Even though we're open scientists, kumbaya, share and share alike, not really. I really don't want to share my data with people. And so that's why, again, I can skip over this, but I live here at LCLS, but I also do machine learning for D3D. And the two give me a nice dual view of how different use cases will leverage our technology. The data rates are about the same. They're not so significantly different. We're in the scale of terabytes per second. We heard from Martin that it's actually about the same scale as the radio astronomy. And so all of these cases are quite interesting. Here it's many more single channels of point detectors, which looks like radio astronomy. So a lot of our solutions, when we look, I'm a physicist, so everything's a harmonic oscillator. So if I can cast everything as a harmonic oscillator across domains, the solutions we come up with will be generalizable. And that's why I like looking at two different domains. The one thing I want to point out, because I mentioned it before, I like to always remind people, I hate dimensions. I want to reduce them as quickly as we can because I believe in Taylor expansion. I believe that I do not want more parameters than I have data points. I want more data points than I have parameters. That bothers me tremendously, which is why I'm a big fan of reducing our dimensionality immediately, as soon as we can, because it not only saves us in storage, it saves the sizes of the models that we require in order to saturate the parameters of these models with the limited amount of data. I know I just said terabytes per second, but we only have hundreds of thousands of shots from D3D. So we don't have the level of data to saturate billion parameters of models with what we have recorded throughout the history of that tokamak. Can't saturate them. And so we need to rethink how we cast our models so that we use things that are leaner. They're sufficiently expressive, but it's in a representation that matters. And I think we get this by finding representations that matter. And the reason I feel like there's a there is nature does it. She's designed hardware inside jumping spider, less neurons than a fruit fly, but can navigate a three-dimensional maze, never getting an error, right? Your pit crews in Formula One racing, they're making split-second decisions. This is what I want to do with AI. I don't need something to try and rationalize why something came out. That's for AGI to do for fun while they're getting, therapy from a digital assistant. I don't need that for science. I need this. I need to make quick, real-time decisions for fusion reactors. We need a pit crew. And luckily, we're working on that. This idea that we apply something reasonably conventional, this is actually just PCA. I wouldn't call it machine learning in principle, right? Because we can update the coefficients or the eigenvectors that we're comparing against. But the thing that I like to present to users is we can do this in a real-time scheme. We can update those coefficients. And this is something that is now, it's an adaptive detector whose eigenfunctions that I'm projecting against to get coefficients can evolve in time. So now I have an adaptive detection system. And that to me is much more like nature. She's learning on the fly. And that's what we want to exemplify. I got to watch my time. I have this favorite detector. It happens to be very close to this radio astronomy case, and that each of these detectors is an electron spectrometer, and it measures high resolution spectra at the LCLS. Each is a point detector. It's effectively reading gigasample per second continuous. And so we need to compress this in real time. Compressing it means I need to somehow interpret these images that it's going to give me. The result of that interpretation is the shape of the X-ray pulse. And it turns out when I'm doing science at LCLS, the shape of the X-ray pulse determines, did I measure a resonant X-ray absorption? Did I actually run a shot that gave me a pump probe signal? Because I don't know how many people here are familiar that what we call an X-ray laser is really kind of a glorified flashlight. It does not look like a synchrotron. It is a disaster of a beam. It looks nothing like a clean pulse. But this allows me to reconstruct what it looked like on every single shot, so I can sort them into sometimes about, say, 20% of the time I get something reasonable. Another 20% of the time I get something that looks like a pump probe experiment. I don't know which ones they're going to be, which shots they're going to be that, but I can figure it out on the fly. Or I can have something wildly complex, and maybe at dinner tonight, you can ask me, what would you do with a stochastic source that is sampling phase space honestly randomly? I think that's where I'm getting really excited about the future of this. But this needs to happen on the fly, because I will do a different analysis on each particular shot depending on which shape showed up that time. These are coming at a megahertz. I have to make these inferences at the microsecond time scale. And hopefully this won't fail. That's not. Oh, it came back right as I slide. There. All right. So we're working on this right now. The idea is we have inference models that are actually composites. The nice thing about working with FPGA teams and looking at things that happen really fast with low latency is you swap out energy for latency. And so I will actually start all of these processes in the FPGA as they come. I don't know yet which analysis is going to be important, but I can figure out from something that's a simple LSTM will tell me, did I have one pulse, something that looked like a double pulse, or this quasi-stochastic field? And so I determine which of the outputs of these parallel operating processes go. So it means I'm designing a composite of machine learning models. They're going to run in parallel, and I'm going to switch on which output in real time. And so that's the way that we're designing so that we can have something that runs in real time. Yes, I'm doing more compute than I need to. It is not a sequential decision. I'm launching them all at once so that I choose the winning horse at the end. And that's the model that we're going with. Again, one of the key features here I highlighted in yellow, we happened to benchmark this stuff on the Grok with a Q inference engine. And when we compile for Grok, we get reasonable latencies. They're not our target, so we have a long ways to go. Remember, I said microsecond here. This is at hundreds of microseconds. And so we still have further to go. But I point out that an autoencoder, this piece of it, right, is a simple autoencoder, CNN. If you use vanilla compiler for Grok, it does not really optimize all that well. It was designed for something. This regressor looks more like a transformer. Grok has optimized their stuff to do transformers. So really good at our vision transformer. We have a fusion project using a vision transformer, not so great at the CNN, but our FPGAs can beat this. So this hints at a heterogeneous streaming environment. Really, some of my images really die, but roughly the point here is that we're now exploring how you can use spiking neural networks to analyze these analog signals, because there's this effort in DOE to look at true heterogeneity, including analog from the sensor itself. And so this idea that, we represent these spectra as spiking neural networks, which then bring you down to a very low bit depth, you can start to make decisions the way nature did, right, with spiking neural nets. And we compare with conventional machine learning algorithm and get reasonably similar results. So that's particularly important to us. What I would say is, in the interest of time, I'll move very quickly. The idea is that you take these results out, and it's not just that I'm writing information to disk for scientists to analyze later. I'm actually turning it around and shaping a laser pulse at the injector so I can modify the electron bunch that produces those X-rays in the end. So now this becomes a breathing accelerator. It's actually moving with me as I start acquiring data. And this notion of actually doing autonomous science and autonomous search becomes a real possibility because we have a feedback system. And so that's something that the student is actually working on. The output of this pulse shape says, oh, science is actually getting more interesting as I change the pulse shape into this stochastic field instead of the pump probe. Let's modify the photo injector laser so we make more of that. And so you have an automatic, oh God, that's terrible. 2 minutes. Skip over that and get to fusion. All right, so what do we need to do, given that this came up a minute ago with Tom, is we have this American Science Cloud. We have to move quickly, and we have to move on these projects that are important, like fusion. LCLS is also important, but we've been essentially told by the administration, you'll do this now, right? And so we have to take what we already have. For instance, we've got some allocation to do trade. This happens to be a vision transformer model that is working on the signals in the D3D reactor. The image is kind of a little blurry, so it's hard to see, but essentially figuring out how can we tokenize this data so we can move it quickly from D3D over here, leveraging existing data in the Fusion data ecosystem, bring it either to Slack to train the weights in the model. I said that we could do this in real time. Here, the FPGA lives at D3D. It's plugged into the data, the live data stream at D3D. We can update those weights in real time, but we can do training at NERSC, for instance. We can also do training of the larger disruption prediction, which is what this ALCC grant was for, at Frontier, and then feed these back with existing infrastructure. And this is the thing that I think is important for us to deal with now is, what do we already have in hand that we just need to plug together in an ecosystem? Because we need to move quickly. I would say multiple views on the same thing. This is a project that we did in our group a couple of years ago, where we looked at multiple different signals in order to get the output. And An ecosystem tends to look like this, where you have tight loops, where you have optical imaging, you have time series waveforms, you have a tight feedback that avoids, for instance, avoids ESNet, it's on-prem. And then you also have the model, the overall model that's going to fuse multi-sensors together to interpret that shot that will then feed back control signals back to the token. And so this, to me, is the ecosystem. It's computation that lives not just at the local site on-prem. It's not just using data, throwing it to HPC and getting it back. It's got local loops, it's got non-local loops, and it's all working in unison. And that to me is what I expect is an ecosystem for compute within DOE. I want to just mention that doing this securely is a project that is happening as we speak. This frontier is blacked out. This is a problem for me now, today, because D3D is a national interest. The data that's produced there, if it hasn't previously been published, is not open. And so we have to work on the moderate enclave here. Currently, S3M, which is their effort to do secure compute at Oak Ridge, is only for the open side. So getting it running on the moderate side is actually critical for us and on the pathway to actually doing this ecosystem. If you want to ask me later why I care about this other company called Kornami, they do fully homomorphic encryption. Now, if I can do machine learning in encrypted space, I now start from a foundation of security. I can give you the keys for open science, but as long as I have a foundation of security, I actually can collaborate with my private sectors a little better because I can preserve IP. My scientists who are actually concerned about getting scooped, they can feel much more comfortable because their data is actually mathematically provably hidden from their competitors. And so I think in this world of competitive science, we need to be mindful of this. We can't fool ourselves into thinking that everybody just wants to completely open up their data. And so, this is kind of a snide remark, how I learned to love. I'm out of time. I'm going to thank my program managers. And in the end, I started out as a philosopher. So this idea of being stuck in a cave and seeing only one way of viewing your data is terrifying to me. I think we need lots of ways of viewing our data, but that means multiple facilities that are distributed across the nation using compute that is distributed across the nation. And that way we can get the necessary orthogonal shadows that help us reconstruct the whole dance of the chemical reaction. So thanks.
We have a little time for questions. Anyone with questions?
Right. So I really like your point about not making like a human brain, but a spider brain.
Yes.
Now, my very naive theory is the way that this works is that nature made 1 trillion failed spiders and one species was able to navigate a maze. And so I'm kind of, my question to you is like, how do I do that with your like data, right? Like I'd have to find a way to do evolution on neural networks.
Yeah, I mean, it's a valid question. We don't have eons to work here.
Right. Yeah.
Right. We have a year. I mean, actually, technically, we have 6 months. Right.
Okay.
We have to demonstrate in 6 months. 6 months to make this work. How do we do macro evolution in 6 months?
Yeah.
And I think the way we do that is precisely that nature didn't make 1 trillion spider species. She started with a fewer number of them, and then they got incrementally better and better.
Right.
So she builds on her foundation.
Right.
We have a lot of foundation.
Right.
We've been doing physics for a long, long time. Right. Much of what we do as far as like information processing, we can ask ourselves, and that's how we came up with this analysis for the fusion reactors. How does the human see the state of the plasma in this data? And now, can I make that pop? Can I do something with my compute that makes that stand out for whatever computational system I'm going to design? So it's more of like an iteration on what's already been done. And so that's how I think we can move faster than nature, is use what we already have. It's similar to physics-informed neural networks, right? I'm not trying to let the network learn all of the physics. I'm trying to put as much of the physics into the early stages of that encoding as I can. That way, my initial latent representation is human interpretable, right? It's reductive. I try to go as far quickly as I can to a binary array to represent the information. And then I only do the, I'm also a firm believer in perturbation theory. So I want to apply known physics all the way up to here, and I only accommodate the unknown with that last, hopefully much smaller network. And that then ideally fits in reasonably fast, low latency inference hardware. And also, we say inference, we say AI because that's the hype. I mean, take out the activation layers and you got linear algebra. So we can do proper math. We just don't want to tell our politicians we're doing that. We want to tell them we're doing AI. So I just remind people of that. Do we have one more?
Yeah, so just follow up on that. So on the inference AI side, edge, what are you currently most bottled? Is it the latency? Is it the bandwidth? Capacity, number of devices? Like what would get you more throughput? It might be complex.
Not relying on batch size greater than 1 to improve your throughput numbers. So change the metric of success a little bit, would start to put the onus on how fast can you flow data into and results out of a coprocessor. Rethink how I feed signals into a coprocessor. Because right now I've got one of the things we're working on is how do I take a camera from, we work with camera companies, particular not our own. I know Yana said that our TID group does our own detectors for X-ray detection, but also working with commercial vendors who have this chicken and egg problem. Why would they have a sensor that could actually do 100 kiloframes per second, but they can't move that data off because they're trying to move every pixel. But also they don't have enough engineering support for, users who only know Python to say, hey, what could I convince you to put on your FPGA on board? They can't support that. But if they could put my analysis on their FPGA, I could reduce those megapixels down to a handful of overlap coefficients, right? That I could take off of the camera. And now I could use their next generation. So the bandwidth, I think, is my bottleneck right now.
But if you had more compute locally, that would help.
More compute, when you say locally, I mean at the sensor.
Yeah.
Yes, at the sensor.
Less compute or less data off.
My problem is, and I will leverage the thing that LCLS does very well and will always insist, we will not compress everything because that's not science. We will leak through at least 1% of the data in as full of fidelity as we can handle, which right now is complete full fidelity, so that you have a solid scientific validation. That becomes your training for how to update this model, which is evolving over time. That training requires your leadership computing facilities. And that's why you have a tight loop for inference, but you have the larger loop to update the models that then are streaming in at the seconds to minutes timescale. And the same thing is true of D3D.
We should go to our